Okay, so welcome to Math 150 Multivariable Calculus. This is lecture 6. So we're going to continue talking about sequences and series, and in particular, when does a series converge? And it's always important to be able to answer the question, why are we doing this? This is actually something I really like about the book, is it's put sequences and series as the first thing we do in multivariable calculus, rather than one of the last things. And the idea is we want to take complicated functions and replace them with simpler functions. Calc 1 is basically about replacing functions with straight lines. Differentiability means locally it's well approximated by a straight line. A generalization of this is going to be how we define a function to be differentiable of several variables. And then we'll get to Taylor series, which will allow us to replace complicated functions with simpler ones that do a great job approximating it. And the more terms you take, typically the better job you do approximating it. There's a lot of functions which you may think you know and you may think you understand, but they're actually infinite series. So if you think about sine and cosine and the exponential function, these are actually infinite series. And so we really need some notion of how they work. Just because we give them a name doesn't mean we really understand what they're doing. They just happen to be extremely common, useful ones. All right. So the first thing is the difference between absolute convergence and conditional convergence. So a series converges absolutely if the sum of the absolute values converges. If my series has non-negative terms, well then if I take absolute values, have I changed anything? So if my series has only positive terms or zeros, does taking the absolute value change anything? No. So if the sequence is non-negative, absolute convergence and conditional convergence is the same. But a lot of times you can have series that alternate. And when the series alternate, then there could be a difference between the two. So as a great example, and this is related to one of the homework problems, let's look at 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 plus dot, 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 dot. And the key to understanding this homework problem is to recognize that this can be written as 1/2 of 1 over 1 minus 1/3 plus 1 over 3 minus 1 over 5 plus 1 over 5 minus 1 over 7, and so on and so on and so on. And the reason is 1 minus 1/3 is 1 over 1 times 3. 1/3 minus 1/5 is 1 over, I'm sorry, it's 2 over, is 2 over 3 times 5. The next one is going to be 2 over 5 times 7. And what we have here is we have a telescoping sum. The minus the third and the 1/3 cancel. The minus the fifth and the fifth cancel. The minus the seventh and the 1/7 cancel. And so if we just add these terms as we go down, the sum is going to converge. But if we looked at the absolute values, if we looked at 1 over 1 plus 1 over 3 plus 1 over 5 plus 1 over 7, do you think this converges or diverges? What do you think? Yes. So this diverges. So how would we prove that this diverges? Yes. Good. So one thing is you could think of it as half the harmonic series, and the harmonic series diverges. And so this should diverge as well. If you want to do it formally, let's let an be 1 over 2n. That's half the harmonic series. That's just the even terms. And now, if we let bn be 1 over 2n minus 1, we have bn is greater than. And so this would be a good comparison test, is I'm comparing it to the series that's half the harmonic. So when you have this alteration of sign, you have the possibility of things canceling. And so if I just put in absolute values, the sum may no longer converge because I have a lot of cancellation as I go along. It turns out if you continue in math, you take classes like real analysis, if you have things that are absolutely convergent, where you can put in the absolute value sign, things are going to be much easier. So everybody should have done Calc 2 by now. In Calc 2, we do integration. In Calc 3, we're going to do integration as well, but we're going to do integration in several variables. And so one of the natural questions to ask is, do I integrate first with respect to x and then y, or with respect to y and then x, or does it matter? And a lot of times the answer is it doesn't matter, so long as the double integral of the absolute value is finite. So stuff like this is very important for justifying some of the things we want to do. We want to be able to say, it doesn't matter which order we integrate, we're going to get the same answer. If you had a bunch of money on the table, it shouldn't change how much money you have, how you count it, right? The total amount you have should be independent of the order in which you count things. That's not always true for sequences in series. For some sequences in series, depending on how we arrange the terms, I can have all the same terms, but get it to have something different. Whenever that's happening, it's because there is, some infinity going on. So one of the standard theorems is that if a sum is absolutely convergent, then it's conditionally convergent. And just the high level key idea is, well, of course, because with conditional convergence, I'm introducing the possibility of cancellation from sign. And so if things converge absolutely, this can only get better because now I'm allowing some cancellation to happen. And so a series is conditionally convergent if the sum of an converges, but the sum of the absolute value of an diverges. You can argue as to whether or not this is a good definition. Can anybody give me another definition of converges conditionally? It's not going to be this definition. It's not going to be the same as this. Can someone give me what else might have been an acceptable definition of converges conditionally? So this definition is the sum converges, but the sum of the absolute values doesn't. What's another possibility you could have had for your definition of conditional convergence? Any thoughts? Yeah. Well, so what I'm saying is this sum converges, and I'm telling you that this sum diverges. That's what it means to converge conditionally. I'm telling you something about the sum and its absolute value.
So if that one diverges, does that mean
Nope, nope. So again,
one gets the final answer and the other doesn't.
nope.
Is the absolute value necessity for divergence? Could you have another function that would diverge from its initial series?
So we're saying this converges, and we're saying something about the sum of the absolute values. We don't need to say anything about the sum of the absolute. You could just say a sum converges conditionally if it converges. We could have just left it as that. They're specifically saying not only does it converge, but the sum of the absolute values diverges. You have freedom in terms of choosing what you want your definitions to be. It's always worth thinking, why do we want this? Well, this way, when we talk about something that's conditionally convergent, if I say it's conditionally convergent, then that means the sum of the absolute values diverges. What's a rectangle? Not,
Well, no.
so some squares, in fact, every square is a rectangle, and some rectangles are squares. So if I tell you, I give you a rectangle, could that rectangle be a square? It could. Just because I tell you it's a rectangle, I'm not being as useful as possible. I'm a math professor, I'm used to that. Would it be nice if as soon as somebody tells you something's a rectangle, you know it's not a square? That's giving you a little bit more information. It's a special type of rectangle. It's a rectangle where the sides are not all equal. Unfortunately, sometimes you might prove that something is a rectangle and you might not know yet anything about the sides. So you have to decide what you want. If I tell you it converges conditionally, I'm also telling you it's the sum of the absolute values diverges. I didn't have to choose that. We didn't have to choose that as the definition. We just decided as a community, that's what we're going to do. It gives you more information. So as soon as you know something converges conditionally, it has to diverge when you put in absolute values. Okay, so we have certain tests to determine if something converges conditionally. So the first is the alternating series test, and this is nice. So imagine you have a sequence of positive numbers. A lot of times we always take the numbers to be positive because whenever you have a 0, does that affect the sum? No, you can have as many zeros as you want without affecting the sum. So I just throw away all the zeros. So we have a sequence of positive terms that are decreasing in size. So each one is strictly less than the previous. And the terms are tending to 0. Well, if the terms don't tend to 0, we know there's no chance that the sum can converge. The alternating series test says the following. If I look at this alternating sum, so B1 minus B2 plus B3 minus B4 and so on, then that sum is going to converge. And so I will try to fix the extra line I accidentally drew over here. See if I can get it. Yeah, okay. So when you're looking at this, let's try to see why is this reasonable. So here's my line. Here is B1 coming up to here. Now I'm looking at B1 minus B2. So B2 is going to pull me down a little bit. Then I have B3, which moves me up. Then I have B4, which moves me down. And let's look a little bit. Can I ever get as high as B1 again? No, because B2 is greater in absolute value than B3. So negative B2 plus B3 is negative. Negative B4 plus B5 is negative. So I know I'm never going to get as high as B1 again. Am I ever going to get as low as B1 minus B2? No, because B3 minus B4 is positive. B5 minus B6 is positive. So when I walk like this, and if I'm trying to see where I'm going, I'm never going to get as high as I used to be. I'm never going to get as low as I used to be. And as I go further and further down, the amount I'm moving is getting smaller and smaller and smaller. And so if I give you something like this, it's going to converge. As an example, sure. So if you look at B2 plus B3, this is negative. If you look at negative B4 plus B5, this is negative. Because we're assuming the terms are getting smaller and smaller and smaller. So if I look at B1, if I group it in groups of 2, subtract something, subtract something, subtract something, subtract something, I'm never going to get as high as B1 again. The other way to do it is I could look at B3 minus B4. That's positive. I could look at B5 minus B6. That's positive. Oops. And so if I look at B1 minus B2, I add a positive number, I add a positive number, I add a positive number. I'm going to be above B1 minus B2. So if I'm trying to see where do I end up as I keep walking along, I go up, I go down, I go up, I go down, I go up, I go down. And as I go further and further along, the amount I move up and the amount I move down is getting smaller and smaller and smaller. And so the motion, the difference between the upper and the lower bound is getting smaller and smaller and smaller. So it's going to converge to something. So if we wanted an example of this, we could do, an is negative 1 to the n over n, or negative 1 to the n plus 1 over n. It doesn't matter if the first term is positive or negative, right? The way they've written it here, when n equals 1, the first term is going to be positive. But I could, of course, start off with a negative term and then go to a positive. So the alternating harmonic series will converge. The harmonic series diverges. That should be our go-to example of something that diverges, the harmonic series. The alternating harmonic series is a very close relation, and that will converge. So what's nice about this is we now have a way to prove a large class of series converge. I just need to know that each term is strictly less than the previous, and they alternate in sign. Do you think that these sums will converge? Absolutely. And if I put in an absolute value, what do you think? Yeah, not necessarily. This is exploiting the fact that I have alternating signs. So it might converge, absolutely. If bn is 1 over 2 to the n, if bn is decaying very rapidly, then it will still converge. But all I need is a sequence of b's that are getting smaller and tending to 0. And the changing sign is going to make everything work. Okay, so now it's time to come up with our various tests. So we talked about screaming babies. Yes. And what do you do when the baby is screaming? I'm sorry, try different things. And after a while, you get better as to which things should you try first. And you start to recognize, oh, this is the I'm hungry. Oh, this is the I need to be changed. Oh, Daddy put on the Red Sox game again, and this is tough to watch this year. The ratio test is one of the easiest tests to use to determine if a series converges or diverges. Think of it as it's similar to the quadratic formula, where it's very mechanical. If I want to factor a quadratic, I could try to be clever and just look at it and see if I'm divinely inspired and see how to factor it. Or I could just say, screw that. The quadratic formula isn't that bad. The roots are negative b plus or minus square root of b squared minus 4ac over 2a. Let me just write those two down. So the ratio test says the following. Assume the following limit exists. The absolute value of an, ooh, that's a bad typo. We'll fix that. It should be an plus 1 as a subscript. Yeah, bad typo. Yes. So we're looking at an plus 1 over an. If rho is less than 1, then the sum converges absolutely. If rho is greater than 1, then the sum diverges. And if rho equals 1, the test is inconclusive. So for example, if I take an equals r to the n, then rho would be the limit as n goes to infinity of the absolute value of r to the n plus 1 over r to the n, which is the limit as n goes to infinity of the absolute value of r. And it will converge if the absolute value, and so this is going to converge if the absolute value of r is less than 1, diverge if the absolute value of r is less than or equal to 1. So in this case, we actually know we'll diverge if the absolute value of r equals 1. So the ratio test at least works in a case we already know. Like I know the geometric series converges for these conditions, and over here, excellent. Now, if we're just using the ratio test, all we would know is the slightly weaker statement that it diverges if the absolute value of r, oops, that should be greater than 1. So that's all we would know. And then we would just have to do by brute force what happens in the special case r equals 1. As another example, let's let an be 1 over n. Then rho would be the limit as n goes to infinity of 1 over n plus 1 divided by 1 over n, absolute value. That's the limit as n goes to infinity of n plus 1 over n. What does that limit equal? So as n goes to infinity, what does n plus 1 over n go to? One. If you think about it, 100 over 99, 1,000,001 over 1,000,000, 1,000,001 over 1,000,000,000. This is going to just go to 1. If you have trouble with this, use an elephant gun. Use L'Hopital's rule, right? Take the derivative. This is overkill. It's fine. And if you use L'Hopital, consider it as a function of n, you would get 1 over 1. All right, so this is equal to 1, no information. And then we didn't do this one yet, but if I give you an equals 1 over n squared, this converges by the integral test. So I'll let you do that exercise. If there's time at the end of today, I'll try to go back and do that. Let's calculate what rho is in this case. And so we get rho is the limit as n goes to infinity of 1 over n plus 1 squared divided by 1 over n squared. So this is the limit as n goes to infinity of n. Oh wait, did I make a mistake in the last one? Yeah, it should be n over n plus 1. Sorry about that. So it should be n over n plus 1. And this one will be n squared over n plus 1 squared. And what does that limit equal? So n squared over n plus 1 squared, what does that go to? It's also 1. So there's a couple of ways to view it as 1. One, of course, is to do overkill, do L'Hopital twice. That's one way to do it. Another way is to say, hey, wait a minute. This is just n over n plus 1 times n over n plus 1. Oh, the limit of a product is the product of the limits. I can just use the last one. So this is also no information. So what's extremely important about these two examples here is it tells us there is no way around the fact that this test is inconclusive when rho equals 1. I can give you a series where rho equals 1 and it converges. I can give you a series when rho equals 1 and it diverges. So there is no way the ratio test is going to be able to give us an answer when rho equals 1. Because if rho equals 1, I can give you an example where it converges. I can give you an example where it diverges. We're going to need something else. But if rho is greater than 1, it will diverge. If rho is less than 1, it will converge, and it will converge absolutely. So the question is, how easy is this test to use? So a lot of it is words like easy are all relative. All right. Are we allowed to consider calculus hard in this class? I think so. This is a calculus class. Calculus can be considered hard. What about algebra? Algebra should be considered much easier than calculus. And this is reducing problems to doing some algebra, to just taking some limits. That's a pretty good trade. Rather than doing a calculus problem, I'm now doing an algebra problem. So if I want to use the ratio test, it's extremely mechanical. I just have to calculate this limit and see what I get. So the question is, why does this work? And so what I want to do is do a quick sketch of the proof of why the ratio test works. So sketch of proof. So if you continue in math, you will eventually get to a real analysis class where they will do this rigorously. They'll roll up their sleeves. They'll do all the cases. What I'm going to do is I'm going to do one case and give you a sense of why it works. You can then try to prove the other case if you want. So let's assume rho equals the limit as n goes to infinity of an plus 1 over an is less than 1. Okay, so there exists an epsilon greater than 0 such that for all n sufficiently large, the absolute value of an plus 1 over an is less than rho plus epsilon, which is less than 1. So what am I doing? Well, here is rho, here is 1. Because rho is less than 1, I can choose an epsilon such that rho plus epsilon is less than 1. Because the limit exists, eventually all my points, they have to be getting closer and closer and closer to rho when I look at the ratio. So since they have to be getting closer and closer to rho, eventually they all have to be less than rho plus epsilon, which is strictly less than 1. And now you can see why I need rho to be less than 1. If rho equaled 1, I'm not going to be able to do something like this, but all of these points are going to be less than 1. So eventually, once n is sufficiently large, an plus 1 over an is at most rho plus epsilon in absolute value. All right, so let's start looking at what's going on. So we would get an plus 1 would be less than or equal to rho plus epsilon times an. Does everybody agree with that for n big? What about an plus 2 in absolute value? What would that be less than or equal to? There's 2 answers I'll accept for this. What is an plus 1 in absolute value going to be less than or equal to? Almost. Say it again. Not a to the, a sub. A sub. So it's going to be at most rho plus epsilon times the absolute value of an plus 1. Because we're saying once you go sufficiently far, the ratio is going to be at most rho plus epsilon. I'm just replacing n with n plus 1. So an plus 2 over an plus 1 is less than or equal to rho plus epsilon. But what do we know about an plus 1? Previous line. So this would be less than or equal to rho plus epsilon squared times an. If we did the next line, an plus 3 would be less than or equal to rho plus epsilon an plus 2. And you should see that this looks very similar to things we've done many times in this class so far. We now just reduce this to something else. Oh, we'll just substitute in from the previous line. An plus 2 is at most rho plus epsilon squared times an. So we get rho plus epsilon cubed an. So if we look at the absolute value of an plus 1 plus an plus 2 plus ... that's going to be less than or equal to, each term has an an, and then I'll have 1 plus rho plus epsilon plus rho plus epsilon squared plus ... Well, what do we know about this? What kind of sequence or series is this? Geometric. And we know that this is equal to 1 over 1 minus rho plus epsilon, as rho plus epsilon is less than 1, so it converges. So we just showed that if you start with a big N and add the absolute values of all the terms from that point onward, you're going to get something that converges. What's really going on is it is a secret comparison test with a geometric series. That's really what the ratio test is. The ratio test is really just a comparison test with a geometric series. And it's just choosing the appropriate geometric series. It's just lurking in the background. So during the pandemic response, people's behaviors changed. People started doing different things. Whenever possible, we tried to do things outdoors. So my family and I took a lot of hikes in Berkshire County. And one of the most interesting ones we ever took was we came across a sign that said secret path this way. Usually they don't advertise where the secret path is and give you directions as to, and here's how you get on the secret path. You come right down over here, and now you'll be on the secret path. Most of the time, they keep these things hidden. When you see the ratio test, when you see the statement, there's nothing here that says there's a geometric series going on. There's just this limit. And if the limit is less than 1, it converges absolutely. If it's greater than 1, it diverges. A lot of math is about pattern recognition. Have we seen anything in our life where if things are less than 1, it converges. If it's greater than 1, it diverges. Yeah, we've seen that actually with a geometric series. This is not a proof that the geometric series is lurking in the background, but it's highly suggestive. And so when we try to prove the ratio test, it turns out what the ratio test is doing is it's just comparing your sequence to a geometric series. And it's just finding a good series to do it. And it is not able to do it if rho equals 1. And that's why it gives you no information. As a nice exercise, try to prove the other part of the ratio test, that if rho is greater than 1, it's going to diverge. So it's a really nice exercise. Try to prove that it's going to diverge in that case. So the ratio test is one of my favorite tests to use. It's very easy. It's just an algebraic limit to calculate. The next one is the root test. This is not as pleasant. It's actually a little bit better than the ratio test. What do you think a little bit better means? And there's at least 2 different ways you can interpret a little bit better.
Yeah, easier.
Good, good. One is that it's easier to use, right? Another could be that it's a little bit more powerful. So if the ratio test says something converges, the root test will say it converges. If the ratio test says something diverges, the root test will say something diverges. But maybe there's a situation where the ratio test gives you no information, but the root test gives you information. So in a situation like that, that would be very useful. And so it's similar to the ratio test. Instead of rho, they're using L, although a lot of books still use rho for both of them. So you take the limit of the nth root of the absolute value of an. If it's less than 1, it converges absolutely. If it's greater than 1, it diverges. If it equals 1, the test is inconclusive. Okay, so I'm not going to go through why this is true. As a nice extra credit, try to prove that this is true. Maybe the arguments we did for the ratio test would be useful. What we want to do now is we want to do some examples and see what can we say. Let's say an equals 1 over n factorial. And let's consider the sum, and goes from 1 to infinity of 1 over n factorial. Do you think this converges or diverges? So this is 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 over 120 plus 1 over 720. What do you think? Converges or diverges? Okay, why diverges?
It's not going to continually get closer to a certain number. Smaller, smaller, smaller.
So the terms are getting smaller and smaller and smaller. Are they getting small quickly or slowly?
Quickly.
So if it's quickly, do you think converges or diverges? Like the harmonic series 1 over n, 1 plus a half plus a third plus a fourth plus a fifth. The terms are going to 0, but they're going to 0 very slowly. Here, the terms are going to 0, but they're going faster than the harmonic. So it might be convergent.
So the speed of how it approaches the number.
Right, the slower it goes to 0, the more likely it is to diverge. The faster it goes to 0, the more likely it is to converge. How could we show if this converges or diverges? What could we do? So we could compare it to 1 over n squared. So if we know, so we could do a comparison test. So if n is big, 1 over n factorial is less than or equal to 1 over n squared, which converges. So how would you show that 1 over n factorial is less than or equal to 1 over n squared? Well, this would be, say, 1 over n, n minus 1, n minus 2, dot, 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 all the way down to 3 times 2 times 1. Versus 1 over n squared. And so you would want to show that when n is really large, this is going to be much less. I think an easier comparison, 1 over n factorial is less than or equal to 1 over 2 to the n if n is big. Is that going to work for all values? Is 1 over n factorial always less than or equal to 1 over 2 to the n? No. If you take n equals 1, you would get 1. 1 is definitely not less than 1/2. If you take n equals 2, you get 1/2 is not less than 1/4. 3, 1/6 versus 1/8. Which is larger, 1/6 or 1/8? 1/6. There are stories, unfortunately, of American consumers who were upset about some hamburger chains that were selling 1/3 pounders and said, why would I want to buy a 1/3 pounder when I could buy a 1/4 pounder at another store? You can't make this stuff up, okay? So 1/6 is greater than 1/8. All right, what about the next one? 1/24 versus 1/16. Ah, finally. At that point, 1/24 is less than 1/16. And the next one, 1 over 120 is less than 1 over 64. So eventually, well, no, sorry, 1 over 32. Eventually, 1 over n factorial will be less than or equal to 2 to the n. And if you think about it, as I go deeper and deeper and deeper, I'm putting in numbers that are much larger than 2. So the denominator is growing much faster. So if I do the comparison test, it works. But for both of these, I had to do some algebra, and I had to be clever in terms of choosing my sequences. What's another way we could try to prove that this sum converges? What's something else we could do? So instead of using the comparison test, we have to be clever. What if I don't want to be clever? What if I don't want to think? You know, I'm not feeling well. I don't have the option of just saying, well, I do have the option, but I felt bad about doing that. Yeah, so I come in to teach. I really don't have the ability to think high. What could I do? What mechanical process could I do? So how else could I determine if the sum converges? I'm sorry? Well, but we don't have a good way to add them. I need a test. You got to give me a test I could use. What test can I use? I could use the root test. What else could I use? Ratio test. Which would you rather do? Take the nth root of n factorial or take n plus 1 factorial over n factorial? Yeah, I'd much rather take the ratio. So let's do ratio. So let's be the limit as n goes to infinity of 1 over n plus 1 factorial divided by 1 over n factorial. That's going to just be the limit as n goes to infinity of n factorial over n plus 1 factorial. What is n factorial divided by n plus 1 factorial? One over n plus 1. Excellent. And as n goes to infinity, what does 1 over n plus 1 go to? 0. So it converges. So this is a great way to compare. We did 2 comparisons, 1 over n squared and 2 to the n. And we also did the ratio test. Which do you think is the easiest? I think the ratio. You know, here I had to play games a little bit, and eventually this works. You know, as you go deeper and deeper in mathematics, you learn how to just wave your hand. Oh, it's dangerous from waving your hand. You just wave your hand, and you can justify and say, oh yeah, if one just does the algebra, this falls out. But you have to do a little bit of work to show for the comparison test that it's going to work, because there's a couple of values that don't work in the beginning. Yes. Sure. So I want to calculate the limit of an plus 1 over an. An plus 1 would be 1 over n plus 1 factorial. An would be 1 over n factorial. So I now have these divisions. Well, if I multiply by n factorial over n factorial, the denominator goes away, and I have n factorial over n plus 1 factorial. What is n plus 1 factorial? It's n plus 1 times n factorial. So the n factorial cancels, and I'm left with just 1 over n plus 1. And I know that goes to 0 as n goes to infinity. Now, there is another test we could use instead of the ratio test. What else could we use? Yeah, the root test, which is right on this page, right? This is not going to be conclusive, but let's see which one is the most pleasant. All right, so let's let L be the limit as n goes to infinity of the nth root of n factorial. So this is the limit, whoops, changed color. So this is equal to the limit as n goes to infinity of n minus 1 dot 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 3 times 2 times 1 to the 1 over n. Oh, I'm sorry, it's not n factorial, it's 1 over n factorial. Right? Who here knows how to take the nth root of that product? Oh, there's a reason I'm your professor. So this expression here is going to be greater than or equal to n halves to the n halves to the 1 over n, 1 over that. Why? Well, if you think about it, what do we have? We have 1 times 2 times 3, all the way up to times n minus 1 times n. I'm going to only look at half the terms. If I throw away half the terms, do I make the denominator larger or smaller? So if I throw away half the terms, what happens to the denominator, larger or smaller? Smaller. So if I make the denominator smaller, what happens to the fraction? It gets bigger. So if I throw away half the terms, I'm going to throw everything less than n halves away. So I've made the denominator smaller. Now I'm going to take the n halves terms that are left and replace everything with n halves. I'm going to replace n with n halves, n minus 1 with n halves, n minus 2 with n halves. I'm making the denominator smaller again. Does that make this larger or smaller? It's going to make it larger. So I'm replacing this product here is going to be greater than this product. N halves to the n halves to the 1 over n. Well, what's n halves to the n halves to the 1 over n? What does that equal?
Why are you just allowed to change it to
Well, I'm saying I can replace this with something that is, I'm replacing this denominator with something that's smaller. And so if I can show that this converges, that dominates this, and I'll be able to calculate the limit. The goal here is to show you that the root test is not fun. What's n halves to the n halves to the 1 over n? So you gotta remember your exponent laws. Yes? It's n halves to the 1 half. The n, you multiply the exponents, n halves times 1 over n is just, so this is just 1 over the square root of n halves. Well, as n goes to infinity, what does 1 over the square root of n go to? As n gets really, really large, 1 over the square root of n halves goes to, well, the square root of n halves goes to infinity. What does 1 over the square root of n halves go to? It goes to 0. So this limit will also have to be 0. Okay, so in terms of ease of use, I think we see that the ratio test just beat the crap out of the root test for this one. You had to be really clever to see how to analyze something like this. Okay. There are other things you can do. There are more advanced tricks you can do to make the root test work, but it's a little bit harder at times. The ratio test to me is the easiest one to use where you don't immediately know the answer. If you know that you can compare it to something that converges or diverges, well, that's the easiest. but you have to be divinely inspired. The method of divine inspiration is wonderful. You write down the answers, I see it works. What's the problem with the method of divine inspiration? At least for most of us. So for the method of divine inspiration, you just write down the answer and say, look, it works. What's the problem with the method of divine inspiration? Well, you just write down and you just show that it works. So as long as you can just write down the answer, you're fine. Well, that's the problem, is you have to be divinely inspired. A lot of it is called experience. The more times you do things, this is the crying baby. I know what to do. I know how to play these games. I've been doing these games for longer than you've been alive. I know how to group terms to make all this stuff work. When you're just starting out, it's much harder to know what to write down. Do I want to compare this to 1 over n squared? Do I want to compare it to 1 over 2 to the n? You can try a bunch of different things. You can also just do something like the ratio test or the root test, which is more mechanical. It then comes down to which limits can you do? Can you do this limit? Yes. It's not pleasant, but I do know ways to do limits like this. And notice I'm doing a lot of approximations. Well, in the end, I get 0. So it doesn't really matter that I've bounded things because, well, if I get that it's at most 0 and it's non-negative, what does it have to be? It has to be 0. So I'm not really losing any information when I do this. Okay, so for homework, we've got a couple of problems on absolute convergence and conditional convergence, and a couple of problems on ratio and root test. So we have a few more minutes. So the last little bit, let's modify the problem we just did. So let's consider e to the x, and when you put a colon in front of an equal sign, that means this is a definition. I'm going to define e to the x to be the sum, n goes from 0 to infinity, of x to the n over n factorial. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. And so my question is, for what values of x does this converge? So what's the simplest choice of x that we could study? So the colon means definition. So when I put a colon in front of an equal sign, this is just a quick hint that this is a definition of something. So can anybody give me an easy value of x to study? You are allowed to be a smartass. 0. Right. If I take x equals 0, there's only one term. Oh, okay, that's not so bad. Can somebody give me another value of x that is easy to study? 1. We just did that a moment ago. All right, so I'll do every other value of x. What test should we use? What test should we use? Ratio. Go to, if I need something, let me try ratio first. And so let's do ratio. And we'll get rho is the limit as n goes to infinity of xn plus 1 over n plus 1 factorial divided by x to the n over n factorial. This is the same as the limit as n goes to infinity. Let's do it slowly. N factorial over n plus 1 factorial, x to the n plus 1 over x absolute value. This is the limit as n goes to infinity, 1 over n plus 1, and I would have the absolute value of x. So x is fixed. As x gets larger and larger and larger, what does this limit, I'm sorry, x is fixed as n gets larger and larger and larger, what does this limit equal? It equals 0. So what do we know? So by the ratio test, since this limit is 0, what do we know? Yeah, converges absolutely great. Not only does it converge, it converges absolutely for all x. This is the definition of e to the x. What should e squared times e cubed equal? E squared times e cubed should be e to the fifth. Technically, if I give you e to the x times e to the y, this is the sum, n goes from 0 to infinity, x to the n over n factorial, times the sum, m goes from 0 to infinity, of y to the m over m factorial. And it turns out that, yes, it is the sum k equals 0 to infinity, x plus y to the k over k factorial. We'll prove this later when we get to multivariable calculus. If I give you 10 squared times 10 cubed, that's 10 to the fifth. It's 10 times 10 times 10 times 10 times 10. It's 5 tens. This notation is highly suggestive that e squared times e cubed is e to the fifth. Technically, however, it's not 2.71828 dot 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 dot, raised to the x power. It's technically this infinite sum. And so technically, if I give you e to the x times e to the y, it's these products of infinite sums. Hey, we're finally seeing something that looks really like multivariable calculus. Instead of doing a double integral, we're doing a double sum. This would be horrible, horrible notation if this was not true. Well, we have cosecant goes with sine and secant goes with cosine. And there's justifications for this in terms of coangles and whatnot. It always bothers me. Right? Notation is not always good, but hopefully it is. Hopefully it's suggestive. Hopefully there's a reason around it. This is the reason for this notation. And this is one of the most important series we will have. And that's technically how we calculate. I think we talked about how we take derivatives and how we need to use this to take derivatives. All right, so this is a good place to stop. So we will continue with various tests, and we'll start getting into Taylor series on Friday's class.